So, good afternoon, students. So, it has been a long time that we have met around 1 month back, and in between, you were having the classes by Dr. Atul Gupta. So, he told me that you have now covered basically the two aspects of statistics. One is the descriptive statistics, in which you have studied these measures of central tendencies, then measures of dispersion, and then you have also covered this correlational statistics, in which you have studied this correlation and regression, wherein you have studied how the data can be associated. That is the association study of the data. And now we are going to move forward for the more advanced features of statistics, which are basically more used in experiments and experimental designing. And these aspects are inferential statistics. That is when you make the inferences out of the given data to you, or whether it might be a sample from a population. You make inferences from the sample and tell that this is the statistics of the population, okay, based on the results you obtain from the data. Okay. So basically, in this series of this inferential statistics, the basic foundation of this inferential statistics has started from the probabilistic theory, and probability is the main pillar of inferential statistics. So today we will be starting this third part, the major part of this statistics, with the chapter probability, on probability, and we will try to learn the basic concepts of this probability. So I will be sharing these lectures once this lecture will be over. And in this probability, what we will be learning? We will be learning about the introduction. Then we will be learning this definition of probability. There are three types of basic definitions about the probability, that is classical or mathematical definition. Then is the relative frequency or the statistical definition. Then third one is the modern definition or the axiomatic approach to the probability. Then we will learn certain probability laws, okay, in which there will be multiplication law and the addition law. And then we will also be studying about the rules of counting, that is how to count the events. So there are three rules: event multiples, combinations, and permutations. And then at last we will be studying a special problem, that is the Bayes theorem, okay, in a special condition. So this is the outline of this lecture, and we may divide this lecture into two sessions. That is, in first session we will be having the class up to 3:45. Then I will give you around 15 minutes break, and then we can have another class from the 4 o'clock. Okay. So starting with the probability, and if we read out the probability statement, so any statement in which there is an element of uncertainty, okay. So basically, this probability is also the uncertainty about the occurrence of some event is called probability statement. So, for example, if we take that India may remain number one milk producer in the world for next 50 years. So in this statement, you will find that there is some element of uncertainty, and India may remain at the number one or may not remain at the number one in the next 50 years. Then there is another statement I have written here, that is, there may be drought in Western India next year. So we are not certain about that thing, that whether there will be a drought in Western India next year or not. So these two statements, and when in a statement there is a element of uncertainty, we call it a probability statement. If in a statement the occurrence of an event becomes certain, then there remains no question of probability. So to probability to calculate, it should have some element of uncertainty. Now we will learn about the another aspect of probability, that is the scale or limits of probability. So what is the on what scale this probability can be measured? So this probability can be measured from 0 to 1 scale, or 0% certain to 100% certain, or in other words we can say that from 100% uncertain to 0% uncertain scale. So the magnitude of probability varies from 0, that is 0%, to 1, that is 100%. That is from 100% uncertain to 100% certain. So this is the scale of probability. So whatever the value of probability you will be getting, it will be between the 0 to 1. Now, probability of an event. The relative measure of degree of certainty with which an event can occur can be termed as probability of the event. That is, degree of certainty with which an event can occur. Okay. So, what is the probability of an event? The degree of certainty with which an event can occur can be termed as probability of the event. Now, there is definition of probability, how we can define probability. And when we define the probability, there are basically three approaches by which we can define the probability. So, what are those approaches? First is the classical or the mathematical definition. Okay, first one is classical or the mathematical definition. Then second one is the relative frequency or statistical definition. Okay. Second one is the relative frequency or statistical definition. And third one is the modern definition or the axiomatic approach to the problem. Okay. So these are basically the three approaches to define the probability, and we will learn one by one that how to define probability in terms of classical or mathematical definition, how to define the probability in terms of relative frequency or statistical definition, and how to define the probability on the basis of axiomatic approach or the modern definition. Okay, so let us start from the classical or the mathematical definition. So before we define the probability in terms of classical or mathematical definition, we need to understand some basic terminologies. And once we will be go through those terminology, we will be in a position to define the probability in terms of mathematical terms. Okay. So what are those terminology? First terminology is the statistical experiment. What is a statistical experiment? Okay. So an experiment having more than one possible outcome is called a statistical experiment. And a statistical experiment, that is, any experiment having more than one possible outcome, is known as a statistical experiment. And a statistical experiment is also known as a trial. Okay, a statistical experiment is also known as a trial. So for example, if we see a statement that sun rises in the east cannot have more than one outcome, if we conduct a trial to find out that from where the sun will rise, okay, because this is a natural truth that sun rises in the east, there is no other outcome of this statement, so it will always be in the east, and because it is not having any other possible outcome other than east, so it cannot be set and considered as a statistical experiment. So the basic need of an statistical experiment is that it should have more than one possible outcome. Okay. Now we will be, if you are having any difficulty, you can write in the live chat box of the YouTube. Okay. So I will come to know that wherever you will not be getting the thing. Okay. So I will try to make you understand. Now, what is an event? Second thing is one, I have already defined statistical experiment. Now we will be studying that what is an event. So a possible outcome of a trial is called an event. Okay, so the possible outcome of a trial is called as event. So for example, birth of a male calf is a possible event at the time of parturition of a farm. See, for example, there is a parturition of a cow. So the birth of a male calf, it can be a possible outcome. A birth of a female calf can also be a possible outcome of this event. Okay, so now exhaustive events. What are exhaustive events? So a set of events said to be exhaustive if it includes all possible outcomes of a trial. Okay, so when we will call an event exhaustive, if it includes all possible outcomes of a trial. So for example, all milking and non-milking buffaloes will constitute inclusion of all female buffaloes at a farm. Therefore, set of milking and non-milking buffaloes are exhaustive with respect to number of female buffaloes at a farm. Okay, so this is the definition. That is when you include everything in a set. So that becomes exhaustive. No other possibility of other event is possible. So it constitutes exhaustive events. Now, what is a favorable event? Favorable event. So, favorable event are such cases that support the occurrence of an event are said to be favorable to that event. Okay. So, if you give an statement and an event is occurring and it is supporting your statement, so in that case, that event is known to be favorable. Now, what is equally likely events? Okay, equally likely events. So, if in a trial the chance of occurrence of any possible event is the same, the events are said to be equally likely. Say, for example, birth of either a male or female calf at a parturition are equally likely event. Say, for example, a buffalo is parturiting. Either a male can be born or a female can be born. So, the birth of either a male or a female are equally likely events at the time of parturition. So, this is an example. Okay. Now, comes your mutually exclusive events. What are mutually exclusive events? So, if in a trial, the occurrence of an event rules out the simultaneous occurrence of any other possible events. Okay, that is, when an occurrence of an event rules out the simultaneous occurrence of any other possible events, then it is said to be mutually exclusive, and the events are said to be mutually exclusive. For example, birth of a male calf is mutually exclusive to the birth of female calf in uniparous animals. Say, for example, there is a uniparous animal which gives birth to single child. Okay, so in that case, if a male has born, then it excludes the possibility that it is a female. Okay, so either a male will born or a female will born. So the birth of a male or a female in case of uniparous animal makes mutually exclusive. Okay, now once we are through these terminologies, that is, we have studied about the statistical experiment, then we have studied about the event, then exhaustive events, then favorable events, then equally likely events, and mutually exclusive events. Now we will define the probability in terms of mathematical definition. So if a trial can result in n mutually exclusive, okay, and mutually exclusive, okay, equally likely, okay, and exhaustive outcomes, and out of which m outcomes are favorable, m outcomes are favorable to an event A, the probability of A is denoted by PA is then equal to m by n. Okay, where m are the favorable events and n are the all the events which are occurring altogether. Okay, where these n are mutually exclusive, equally likely, and exhaustive. So, for example, I am taking here an example. A fair dice is thrown. what is the probability that either 1 or 6 will show up? In this example, discuss various terms involved in defining mathematical probability. Okay, so we will be defining the various terms involved in this statement, this experiment. We are conducting an experiment where we are throwing a fair dice and we want to find out the probability that either 1 or 6 will show up. What is the probability? Okay, it should not be 2, 3, 4, 5. Okay, either 1 or 6. So here, what is the statistical experiment here? Here the statistical experiment trial consists of throwing a fair dice and observing the outcomes. Okay. And what are the events? When we throw the dice, the possibility of occurrence of various outcomes like either 1 will come or 2 will come, 3 will come are said to be events. Now, how many exhaustive events are there? The set 1, 2, 3, 4, 5 and 6 consists of exhaustive events and includes all possible outcomes of this trial. Okay, this is statistical experiment. It means how many exhaustive events are there? N is equal to 6. And what are the favorable events? The set of this 1 and 6. Okay, if 1 is had come or 6 come, it makes the favorable events that support the occurrence of an event as per the condition given in the trial. It means your M is equal to 2. And what are equally likely events? Each event in the set, that is 1 can come, 2 can come, 3 can come, 4 can come, 5 can come, 6 can come. So any value can come and every value have equal chances of occurrence, and hence these events are said to be equally likely events. And how these are mutually exclusive events? Each event in the set does not affect the occurrence of another event and hence known as mutually exclusive events. That is, if 1 will come, others will not come. If 2 will come, others will not come. The 3 will come, others will not come. Like this. So they cannot occur in conjunction. Okay, and hence they are mutually exclusive. Hence, as per the mathematical definition which we have studied above, PA is equal to M by N, and because M, that is occurrence of 1 or 6, counts to be 2 divided by how many total number? 6. So it comes out to be 1 by 3. So this constitutes the probability. Okay, and this completes our mathematical definition of the probability. Now comes your relative frequency or statistical definition of the probability. Now we need to understand this with some examples, and we will be studying these. So the probability of getting a favorable event in a repeated trial. So here what is important is, okay, what is important here? Repeated trial tends to stabilize after a particular number of repetitions. Okay, I am reading it again. The probability of getting a favorable event. Okay, if we state that this is our favorable event and we repeat that statistical trial, then the probability of that favorable event tends to stabilize as there are number of repetitions increases. Now, the number of times an event occur is its frequency. When we conduct a trial one after the other, so how many times we have conducted it, it is known as its frequency. And when this frequency is divided by the total number of trials, that is, say for example, we conducted an event 100 times and out of that we get the favorable event 50 times. So our probability will become 50 by 100. So when it is divided by total number of trials, we get the relative frequency of that. And this relative frequency is nothing but the probability of occurrence of that favorable event. So let us see how. So according to the relative frequency distribution, relative frequency definition, when the number of trials becomes sufficiently large, okay, when the number of trials becomes sufficiently large, the relative frequency of an event tends to a limit. The relative frequency of an event tends to a limit, that is it gets stabilized, and this limiting value is the probability of the event under consideration, and this limiting value is the probability of the event under consideration. Now we will just try to understand this with an example. Okay, suppose we repeat the experiment of parturition in cows and observe the number of times a female cow is born. Okay, as we all know that the probability of getting a male or a female calf is 0.5 or 1 by 2. So let us conduct this trial, okay, and let us see that from a parturition, what is the probability we will be getting. Okay, now we shall find that as we increase the number of observation on parturition from say 10 to 100 and then 100 to 1000 and then 1000 to 10,000 and so on, the relative frequency of getting a female calf will gradually stabilize at 1 by 2. This is the beauty. Okay, so now try to understand from this table. Let us we start the trial. There was first parturition and there is a male was born. Okay, so cumulative frequency of favorable event will be 0 because we are considering that female. Okay, so the probability of the event remains 0. Okay, then when there was second parturition, then a female is born. Okay, then it becomes 0.5. Then after 50 such parturition, we have found that there were 29 females have born. So in these 50 parturition, our probability of getting a female child, a female birth, comes out to be 0.58. Okay, now when this increases to 100, now this on 100 there was a birth of a male, and in total we get 41 females, so our probability decreases to 0.41. Then at 5500 parturition we see that 2710 females were there, and hence the probability was 0.49. But when we increases this number, we were getting these females, but the probability gets stabilized at 0.5. Okay, now so from this experiment, as we increase the number of trials, because initially when we conducted the trial, the frequency was fluctuating, but when we increase the number of trials, the frequency gets stabilized, and that is the natural frequency of that phenomenon. And hence, because of this, we tell that the probability of getting a male or female is 0.5. Okay, let us understand this with how we define this in the form of formula. So mathematically, if n is the total number of trials out of which an event A occurs m times, the probability of A is given by limit n tends to infinity m by. Okay, so let us understand this with a figure. In example 2, we have a case of parturition and whether a male or female has born. Now we just simulate this with another example, and example 2 can be compared with the probability of getting a head. Let us flip a coin and let us find out that how many times we get a head. So it can be compared with the probability of getting a head. Okay, there was a case of male and female, and now we are considering the flipping of a coin. Okay, tossing of a coin, and when we are tossing a coin, so we are just comparing the probability of getting a head. So as we increases the number of throws, the probability of getting head out of the total throws tends to be 0.5. So same can be appraised from the figure given below. So if you see this figure, so this is the proportions of head. Okay, let's say for example it was 0 initially, then it increases, decreases, increases, decreases like this, and finally it gets stabilized at a 0.5 value. So what it tells that when we increases the number of trials, the actual frequency of occurrence of that phenomenon can be, and this is nothing but the statistical definition or the relative frequency definition of the probability. Okay, now we will be coming to the modern definition, which is the combination of this mathematical and the statistical definition. Okay, And this is the modern definition, axiomatic approach to the probability. Okay? And the axiomatic approach to the probability can better be understood after going through the problem. So before we define the axiomatic approach to the probability, let us have an idea about some of the terminologies which we will be using in this modern definition of the probability. Okay, so what are these terminologies? First will be the sample space. What is a sample space? Okay, so it is a set of all possible or exhaustive outcomes of a trial. So the sample space of a trial can be denoted by S. Okay, you can denote it by S, and is given by E1, E2, En, where E1, E2, En are n elementary events, and these all constitute the exhaustive events. Okay, that is, no other events is possible after these events has occurred. Okay. And the sample space can be of ordered pairs, that is, two events can be clubbed together. Okay, or it can be finite or infinite depending upon whether it consists of finite or infinite number of elements. Okay, now what is an event? So an event is any subset of the sample space. Out of those total samples, a subset which we are considering, okay, is called as event. Okay, now occurrence of an event. So event is said to have occurred when the outcome of a trial belongs to the relevant event subset. Okay. Now what is the definition? So according to the modern definition, the probability of an event denoted by PA is real valued set function that associate a real value PA corresponding to any subset A of the sample space S. Okay. So what are the different restrictions on this probabilistic theory? So the probability of an event A in a sample space S is a non-negative real number. Okay, it should be non-negative real number, and it should be less than or equal to unity. So what it is saying here, that the probability of event is lies between 0 and 1. Okay, including 0 and 1. The probability of an event that is certain to occur is unity. Since S is certain to occur, it implies if we take the probability of all the sample space, then the probability becomes 1. If A1, A2, A3 are mutually exclusive events in a sample space, that is, out of the total samples, A1 is an event, A2 is an event, A3 is an event. So P A union A2 union A3 becomes equal to PA1 plus PA2 plus PA3, but provided that these events should be mutually exclusive to each other. So the above relation can be generalized to any number of events. Okay, so simply this PS is equal to summation of PEI, that is where E is an event. If we add all the probabilities of all the events, then it will come out to be. Okay. Now let us understand this with an example. In a game of cards where a pack contains 52 cards. Okay, if we play cards, so we know that it is a set of 52 cards, and there are four categories exist, namely spade, club, diamond, and heart. Okay, if you are asked to draw a card from this pack, what is the probability that the card drawn belongs to spade? Okay, how to solve this? Okay, using the modern approach. So solution is, you make a table, you do these probability questions like this only, otherwise you will get entangled, and you will not be able to understand that how to find the real answer. So it is always better to make these tables in probability questions, so the things become very easier. So there will be events, then notations we will be using, and what is the probability of the favorable event. So event is favorable events is denoted by M, and what is the favorable event? A. that is getting a spade. So how many spades are there in a 52 cards? 30. So here we have marked it 30. Okay. So what is the favorable event? 30. And what are the total possible events? N. So it is 52. Okay. Now your probability will be P is equal to M by N. So it will be 13 by 52 is equal to 1 by. Okay. Now in this particular example, what is the probability that the card drawn belongs to either a spade or a club category? So now comes your union. Okay, that is when we say or, so it becomes union. And because spade does not affect the clubs, okay, these are mutually exclusive events. So as per our definition, PA1 union A2 will be equal to PA1 plus PA2 because these are mutually exclusive events. So what is A is getting a spade and B is the getting a club. Okay, so A is about the spade, okay, and this B is about getting the club. Okay, so how many favorable events are there? 30 in case of spade, and in case of club it is 13. Total possible events are 52, 52. So the probability of these two will be 13 by 52 is equal to 1 by 4, and similarly in this 1 by 4. And so what will be the combined probability of either a spade or a club is PA1 union A2. It will be 1 by 4 plus 1 by 4 is equal to 1 by. So this is how we define this case. Now comes your probability laws. Okay, so there are certain notations which are used to be understood before we go for the probability laws. Okay, and let us first understand. If A and B are two events, okay, then PA union B, this union is also known as PA plus B, okay, denotes the probability that either, the words are very important in case of probability, either, and another important word is here is or, and another important thing here is plus, okay, and another important thing here is this union. Okay, if you get this union or plus or either or you have to use this thing. Okay, that is A occurs or B occurs or both occurs simultaneously. Okay, it can be interpreted as the probability of occurrence for at least one of the two events A and B. The symbol union above represents union. Okay, it is termed as union between the two events, and read A union B as A union. Okay, similarly, this PA intersection B. Okay, this when we invert this U, so it becomes a intersection, or PAB denotes the probability of simultaneous occurrence if two events occur simultaneously. Okay, that is occurrence of both A and B at the same time. Okay, so you remove this word, it should not be. Okay, so and it is read as A intersection. Okay, so when it is intersection, then these two events occur simultaneously. So then what is this E slash B? So this denotes the conditional probability. What this tells? This tells the conditional probability. And what is that condition? This means that PAB denotes the conditional probability of the occurrence of A given that B has already occurred. Okay, so this constitutes your conditional probability. So we have learnt about the three things. One is A union B, another is A intersection B, and third one is PA slash B. Okay, so this is the conditional probability, it is the simultaneous occurrence, and it is the either occurrence. Okay, so these are the three things we should understand before we go for this laws of probability. Okay, and in this laws of probability, first law is the multiplication. Okay, so this particular law of probability states, this law states that the probability of simultaneous occurrence of two events A and B is equal to the product of the probability of A and the conditional probability of B, given that A has already occurred. Okay, or the probability of B and the conditional probability of A, given that B has already occurred. So let us understand these things. So PA intersection B is actually equal to PA into PB when A has already occurred, or PB into PA when B has already occurred. Okay, that is the conditional probability of A and probability of A into conditional probability of B when A has occurred, and conditional probability of B into the probability of B into conditional probability of A when B has already. Okay, so this from this formula we can say the conditional probability of B when A has already occurred can be equal to PA intersection B divided by P. These are simple algebra, so we have taken this PA below this PA intersection B. Okay, and similarly this PA slash B, that is the conditional probability of A when B has already occurred, can be calculated as PA intersection B divided by B. So simple to learn which is in the down. If in the downwards A is there, so in denominator A, probability of A. If in this conditional probability of B has already occurred, then in denominator this B. And using the Venn diagram, you should understand this is the total sample space in this rectangle in which A and B are the two events. Then this shaded portion, okay, which is common to A and common to B, constitutes your PA intersection B. Okay, that is simultaneous occurrence of the A and B besides A. Okay, so now let us understand this thing using an example. Okay, so one card is drawn from the pack of 52 cards, and the card is not replaced in the pack, and another card is drawn. Okay, what is the probability that both the cards are spilled? So what we did here is that we have taken one card and we did not replace it. Okay, and then we take the next card. So now the person is asking what is the probability of getting a, okay. So first event, that is we are taking out the card for the first time. So one card is drawn, find the probability that it is a spade. So possibilities, how many possibilities of getting a spade are there? 30. So what will be the probability? 13 by 52 is equal to 1 by 4. Okay. And if we take the intersection of this, that is the opposite of this, when A has not occurred, this is 39. 39 divided by this 52, 3 by 4. If we add these two probability, it should come out to be 1. So it completes our sample. Okay. So here the important thing is this green part. That is we got the probability of A of getting a spade as 1 by 4. So thus PA is 1 by 4. Okay. Now second, now again without replacing that card, we are again drawing a card and finding that whether it is a spade. Okay. So it has to be calculated like this. That is probability of getting a spade when A has already occurred. Okay. So now how many spades are there? Earlier there were 13 spades, but now there are 12 spades. And how many total cards are there? 51 instead of 52. So this conditional probability of B when A has already occurred comes out to be 12 by 50. Okay, so this is not required, this is the complementary thing, that is if this doesn't occur, so again you will see that this is 39 and out of 51 if you will add these up, so the total probability will again come out to be 1, just to check. Okay, so the conditional probability of B when A has already occurred comes out to be 12 by 50. So according to our formula, this P A intersection B should be equal to PA into P conditional probability of B when A has occurred. So this is 1 by 4 into 12 by 51. So it comes out to be 3 by 50. So 3 by 51 is the probability of getting two spades consecutively from a deck of 52 cards. Okay, so this is how this formula of intersection or the law of multiplication solves our problem of probability. Okay, when it asks us the probability of occurrence of two events if it is dependent on the other. The first one is dependent on the other. So if two events are mutually exclusive, what will happen? So in that case, if another card has to be drawn, okay, then this PB will not be affected by this occurrence of the A. So it will equal to PB. Okay. So in that case, it will simply be the multiplication of PA into PB. Now let us see another example to define this thing. One card is drawn from a pack of 52 cards and the card is replaced in the pack and another card is drawn. What is the probability that both the cards are spade? Okay. Earlier we were not replacing. Now we have replaced it. Okay. So again for the first event it is 1 by 4. But for the second event, because now it has become mutually exclusive, it does not depend on the occurrence of the A. Okay, so this BA will be equal to B. Conditional probability of B now does not depend on the occurrence of the A. So it is simply B. So it will be 13 because now there will be 13 spades. So again this probability will be 1 by 4 and hence when we will be using this formula, so conditional probability needs not to be used and simply PA intersection B will be equal to PA into PB, which is equivalent to 1 by 4 into 1 by 4. So it comes out to be 1 by 60. Okay, so I think from these two formulas now you get to understand that how to find out the probability in case of the occurrence of the events, that is A intersection B. Okay, now another example to make you more understand about this concept, a card is drawn at random from the deck of 52 cards. What is the probability of drawing an ace of diamonds? That is, it should be diamond and it should be a ace. Okay, so now this PA intersection B is the probability of the A into probability of B when A has already occurred. So what will be the favorable event? First we have to find out the ace. So how many total aces are there? 4. Out of that 1 will be drawn. Okay, so the probability of A will be 1 by 4. Now when ace has already been drawn, okay, so what is the probability of B that out of the total 13 these diamonds, it will be of 1. So it will be 1 by 13. So what will be the PA intersection B? Because these two events are mutually exclusive. Okay, diamond does not affect the ace and ace does not affect the diamond. So it will simply be the multiplication of these two, 1 by 4 into 1 by 13. So it will be 1 by 52. From here you can have a generalized statement. If you take out a ace of diamond, it can only be one card out of the total. Okay, you cannot have two ace of diamonds. Okay, so the total possible will only be one, and from how many cards you will be drawing? 52. So this answer is correct. Okay, so this is an example of here this b by a is actually equal to this b. Okay, these are mutually exclusive. These are mutually exclusive. Okay, so this solves this problem, and we have only one more small example. Two cards are drawn with replacement from the deck of 52 cards. What is the probability that first card drawn is spade and the second card drawn is a diamond? Okay, so one should be of a spade and another should be of diamond. So again, these are mutually exclusive events. So this PA intersection B will be PA into PB. That is, the occurrence of the B does not affect the occurrence of the A, and these are being drawn simultaneously with replacement. Okay, sorry, with replacement. So it will be 13 by 52, 13 by 52. So it will again be PA intersection B will be 1 by 4 into 1 by 4. So it will be 1 by 16. Okay, these are mutually exclusive. So this is how we apply the law of multiplication to solve the various situations in this probability. And here I will be stopping this lecture, this session, and we will again be reuniting at 4 o'clock with the next session, and we will start from the law of addition in probability. Okay, so thanks for your patience hearing, and it is all from here now. So we will again be meeting you at 4 o'clock. Okay, thank you.